Hi everyone. In this session, we're going to look at discretizing mesh surfaces into strips. This exercise is going to basically yield into kind of a transformation of our original minimal surface geometries into this sort of unrollable strip surfaces. So for this one, I'm going to work on the triply symmetric gyroid that we built. So this one, I'm going to process this to show you kind of the overall workflow, how you can develop this into individual pieces that are suitable for manufacturing. So I'm going to isolate this on my Rhino file. And if you remember, this was the in the previous video, we covered how you can load this up. And let me actually hide this version, move the wireframe. Okay, let's set true. And we were basically doing some kangaroo relaxation and form finding experiments here. So I just lowered the resolution of the mesh subdivision from 3 to 2 so that we get less faces. But if you increase this, you would basically get more surfaces eventually relaxing through the simulation. And then the stripper plugin that we're going to look into, it will basically divide this up into more elements. So in order to optimize the number of strips we're going to work with, I'm going to reduce this to 2 and rerun the simulation. And this is the kind of geometry we'll be using for this exercise. So I would recommend first to bake this so that you can split it from the existing script. One reason for that is because this is running a physics simulation, so you don't want this form to change. So after we do the form finding, we just want to work on the surface topology and just develop it for manufacturing. All right, so I'll just move here and show you a few mesh operations that we will be using. So first let's look at our mesh boundary. So if you go to the mesh here and then look at face boundaries, these are our mesh faces. And what we want to do is essentially the way we built this is out of quads, right? So the quads can be divided into rows and columns. And there's one tool that can do it pretty efficiently, which is called a stripper. And the stripper function can divide the surface, in this case the mesh surface, into curvature directions and give us the mesh construction or the strips. So we're going to look at first the topological directions. So I'm going to write topological directions. So this is the command to get mesh topological directions. If you supply this in, you need essentially 2 Boolean toggles here. So let's connect them as well. So this will give us basically kind of the perpendicular directions of u and v directions. So these are this is basically how the quad information is flowing along the surface. And the O and the S parameters, they basically control how these strips are divided. So these curvature directions, right now you can see they're a bit more patched, so we don't get kind of linear distribution of elements, but they're kind of it's kind of like a patchwork. So if you toggle with some of these tools, you can see that their directions or calculation is actually changing. And what we want to do is make the reordering to be true, so that it kind of first fixes the direction of flow in the input mesh so that we get kind of nicer strips like this. And this is actually the U direction isn't changing anything. But basically what we can do is you can actually change to the perpendicular direction here, and that will basically give you the opposite strips. So the next step will be direction. Get strips via directionals. So for this one, you would use the recomputed or the sorted mesh. And then if you supply any of these curve directions, you would basically get the mesh split into strips. So if you bake this to look at it, you can see that these are now extracted as individual strips. So we're going to actually visualize how this geometry is being distributed. So the first thing I want to do is smooth these mesh boundary edges. So I'll just connect the mesh faces, and then we can basically apply multiple levels of smoothing, which will kind of alter these strips. And let me actually hide some of these as well, so that we are left with the kind of final construction. You can see it's kind of almost like doing an inset of the mesh strip. So let's look at here, the intensity between 0 and 1. So that's kind of how much smoothing we want to apply to the mesh. And if you do 0, it remains the way it is, and you can apply multiple levels of smoothing, but eventually it will basically shrink the strips. So what we want to do is maybe create some gaps, but essentially if you want to make connections along these boundaries, you may also not use the smoothing operation at all, because then we will have issues connecting these meshes with each other. So I'm just going to move it aside. The other thing we can look at is we can do kind of an offset, outset mesh boundary edges, so we can look into that. So if you use that one, then you can give it kind of a negative and a positive threshold. So we can do -1 to 1. And this will be basically like an edge offset in our case, right? So knowing that this is how this mesh is kind of transformed, maybe we can use this distance again to make connections here later on if you want to maintain this sort of gap between the strips. But essentially, smoothing kind of gives you symmetry curves, but this gives you kind of an offset of the mesh boundary. Okay, next thing is I want to visualize these strips. So we can use custom preview. So we can get the individual geometries and then attach a color swatch. So let's say we want to attach just white, and that will visualize our geometry for us. So I'm going to hide some of these geometries here. And we can also hide the topological directions. So something like that. All right, that looks pretty good. If you want to kind of identify these strips individually, then one more thing we can look into is basically coloring them differently. So for that, we could do a color gradient. And if you right click to the color gradient, go to presets, you can use some of these color presets, like this one kind of gives you like a rainbow distribution of colors. And these could be individually assigned to each strip so that we can differentiate them easier. So in order to assign them, we have 24. So I will just do a 0 to map the first strip on the left end of the spectrum. So the L0 and L1, they basically bound the spectrum here, and the T is your parameter. So if you have, let's say, 24 elements, you can do a list length, get number 24, do the series. So this will become my T parameter. So you can see it's going from 0 to 23. And what I want to do is here, you can just use L0 to L1, so L1 could be 23, but you can also just plug in the list length here, and maybe you're kind of omitting a color here, but that's kind of okay. And if you supply this, you'll basically get kind of each strip colored individually, so that you can kind of identify them once we start unrolling these pieces. Okay, so the next thing I want to do is essentially just show you how you can unroll these and distribute them, so that we can actually assign the same type of coloring. So for that, we need like an unroller function. Now for this assignment, I did like a look at different types of unrollers, and there's this one, which is the open nest unroll. This one could be useful, but it actually didn't work for the mesh directionals that I wanted to use. So when I used this one, let's see, it kind of gives me this sort of unrolled geometries, but they're kind of also broken in a way. So if, for instance, let's go through this list. I'm going to do list item and 0 to 25. So you can see the 0 index. Actually, maybe we should just do flatten first. It's giving me a lot of untrimmed surfaces as well. So something isn't converting these 24 meshes in the right way. So we want to get essentially faces of 8 quads and 40 quads. But this kind of didn't work in this case. So I went ahead and wrote a custom unroller function. I'll just grab it from another file here to kind of show you. So this is the function I used. So this will be shared with you. So if you come back here, what this does is it's essentially just a C# code that converts our each individual mesh faces into B-rep geometry that could be unrolled. So it's as if we're converting each mesh individually, and then we are kind of converting them into B-reps, and then each B-rep is unrolled individually. So let's see, this is going to be assigned to these meshes here. And what that does is, if you look at the output geometry here, they kind of give me all the strips individually. So these are open B-reps still. So it's as if we baked these meshes. So let's say I grab this mesh. I first do a mesh to NURB, because we cannot unroll the mesh. And then this one can be unrolled, right? So without exploding it, and that will give you this type of strip. And I'm basically automating this sort of operation. So I'm just converting each mesh into a B-rep, a boundary representation geometry, and then unrolling them individually. And then this could be processed for manufacturing purposes. Okay, so once you have these, you can see they're kind of not in a discernible order. So what I want to do is kind of spread them around. So for that, you can actually do like a grid if you want. Let's do like a grid structure, or you can just create an array. For instance, I can take these and create like a series, and we can basically space them out in X or Y. Or if you know how many pieces you have, let's say I have 24 pieces here, I can create a grid of 4 by 6. So first, initially, we will be basically spreading these elements. So let's find out where the grid is. So I'm going to go to this vector grid, and I want to create a square grid, and base plane is X, number of cells in X and Y, well, it's 5 by 5. So what we could do is like maybe create a grid of 4 by 6. And I can do a grid size of, let's say, 500. Well, that's too big. So let's shrink it a bit. So what I want to do is place each of these elements inside of these grid cells so that we can process them individually. Okay, so I'm going to do 60. And these will have areas. So they will have like a centroid. And essentially what I want to do is move the centroid of these geometries. Move these geometries using their centroid to these target places. So I want to do a move, and we need a translation vector. So we can do a vector 2 point. So I want to move from this centroid to this centroid, and this needs to be flattened. So we have 24 vectors, we have 24 geometries. So if you connect these two, they will now be placed on individual grid cells. Now let's assign the same color mapping to our unrolled geometries. So if you plug them in here, now you can see they're kind of color coded, so we can know where they sit inside of the geometry. But also we can create kind of an annotation tag. For instance, if you did annotation dot, if you went back to our initial mesh here, we zoom in, and this one I can just do, if we do an area, it may not be on the mesh. So one way to evaluate the mesh would be to kind of look for a point on it. So let's see what we get when we do area. So area doesn't give me a point on the strip necessarily. We also do have mesh eval, which evaluates a point on the mesh. But in this case, we may not be able to get that either. So maybe we can do is we can deconstruct mesh, and we can look at one of the faces. So we can just grab the first mesh quad of each of these meshes. Then we can look at the area. Let's see if it doesn't give me the area because let's see what kind of information we have here. So I'm trying to find like a point, but it's just giving me the quad. So I'll just do construct mesh, or we can also do, well, probably we need to do deconstruct face so that we get these individual points. And then if you do a list item and access these indices of vertices from the mesh, they will give you a corner point. But essentially what we want is two opposite corners. So it could be from A to B. Let's see if this will give me a line. Yeah, it's kind of giving us a line. So I want to place, let's say, a tag along each strip. That will be kind of at the midpoint of it. So point on curve. So that's kind of the point where I want to place an annotation dot. So that will be the location. And we can give kind of a primary text, which could be just a series. So we have basically 23 strips, but we can start from like 1. We can also give it like a code. For instance, you can use list length again. Starting value, you can do 1. And we can also do text join. For instance, you can create like a word. Let's call it st or s, and we can duplicate this text by the number of strips, and then we can do a merge. We want to merge this code with the number. Let's actually put an underscore as well. So that's going to be, let's see, that's the number. Okay, and then we want to graft both of these. So they're put in clusters, and when you do text join, that will basically give you kind of an ID tag for each individual strip. And depending on how you want to manufacture this, you might have different types of IDs, like different types of lettering. For instance, this could be just S. And we can then place these as annotation tags on the geometry. So now you would basically have a tag for each individual piece as well. So I'm just going to move it aside and turn it off. But we can also do the same for the unrolled versions. So all I have to do here is update the location. So the location would be my centroid. So now what we have here is if I bake these annotation dots, and let's say, let's see, the numbering is kind of incorrect, I guess. Okay, because of the grid size, we got multiple annotation dots, so this needs to be kind of correlated. So let's do, let's create like a point grid here, and put the locations here, but grafted. So that works. Okay, so I'm going to bake these dots. I'm going to bake these dots as well. Now, if you want to bake the color, you need kind of like a tool. I think Lunchbox has object bake. So what we can do is we can get the geometries as objects, and then these could be the object color. And then if you do a Boolean toggle or a button, I think the button also does it. If I bake these, they should have colors on them. So now if I move it around, move to rendered mode, maybe shaded mode. Yeah, the shaded mode has the coloring. And let's see. This is the mesh faces. These are the object colors. Do we have material? I guess we don't. It just gives it kind of a shading. But let's bake them again. Move it around, and you can basically have this sort of coloring baked into the geometry itself. And then if you bake it with the annotation dots, then essentially we have like an ID tag, both the name of the strip, but also kind of a color to orient us basically inside the geometry, which will be helpful in manufacturing later on. And we can do the same thing here. So I'll just move this around, and we should correlate the same information for the unrolled geometries as well. So if you bake these two, and these tags are baked, so what's happening now is we have the geometry basically unrolled with its ID and the color, and the geometry in the 3D configuration. So we kind of need both of these because we want to build this piece out of, let's say, a flat material, but then we want to know its placement inside the object so that we can put it together with everything else around it. So these IDs kind of help you figure out like what is adjacent to which piece, right? So they're not in a discernible order right now because we didn't sort them, but you can see like S22 is adjacent to 23 and 13. So we have to connect these maybe inside first as groups so that we can put the whole thing in assembly later on. But eventually we will build on top of this. But yeah, this is kind of the overall workflow. So you can start with a mesh, get the topological directions, and then unroll these geometries and kind of coordinate the coloring of these objects along with kind of annotation tags so that we keep track of the information per piece, and we'll be able to put them together this way. Okay, so that's kind of an overall view of the stripper plugin and the unroll sequence. I hope this will be helpful for digital fabrication workflow. Thanks for watching the video, and if you're visiting this channel, please consider subscribing and liking these videos. It helps grow the channel. So I'll see you in another video looking at how to basically alter these edges boundaries for connectors. Thanks so much.